Hello and welcome back. This is a re-recording of the first video of section 4.2 since the first one didn't save correctly. We'll begin with some vocab. So we've already seen what a simple event is. It's essentially just any outcome of a procedure that can't be broken down into smaller events. And a compound event, new vocab, is going to be any event that combines at least two simple events, so two or more. So for instance, if we roll a die, this is our procedure, one event could be getting a 6. This is going to be simple. We can't break down getting a 6 into any smaller events. However, getting an odd number, this is not going to be simple, and this is in fact going to be a compound event. And why is that? Well, to roll an odd number, you can either roll a 1, a 3, or a 5. So because there's essentially 3 different simple events, getting a 1 is a simple event, getting a 3 is a simple event, getting a 5 is a simple event, getting an odd number is the combination of 3 simple events, so it is a compound event. So to look at compound events, what we're going to do is we're going to look at all sorts of probabilities. So let's start with two events, which we'll call A and B. They can either be simple or compound or anything else. So it's just any two events for a procedure. We saw last time the notation for the probability that A occurs is P of A. And what might make sense is that the probability that A or B occurs is just written as the probability of A or B. Now, in mathematics, OR is what's called an inclusive OR. So let me describe what this means. So the probability of A or B means that the probability that A happens, or B, or both simultaneously. In everyday English, we normally don't include the option for both. For instance, if you were offered some pie or cake for dessert, it would quite often be implied that you have to choose one or the other. In mathematics, OR means that you can choose both. So we want to, so the probability that A or B, the probability that either A happens or B happens, or they both happen. Now, the probability that they both happen, we can write that individually as well. So this is the probability that A and B occur, meaning they both occur at the same time. So we'll have some tricks for calculating these guys. But for the moment, let's just do an example that'll be fairly simple. So let's roll a die, and we'll call A the event of rolling a 4 or higher. So this means that A occurs if we roll a 4, or a 5, or a 6. And the event B is going to be roll an even number. So B will happen if we roll a 2, a 4, or a 6. So we can calculate the probability that the A occurs. Since each outcome of since each roll of the die is going to be equally likely, there are 3 ways to roll a 4 or higher, and there are 6 sides to a die. So there are 6 different simple events. So the probability that A happens is going to be 3 over 6, which we can simplify to 1/2. The probability that B occurs, so again, B, there's 3 ways for B to happen, and there are 6 possible dice rolls. So the probability that B happens is going to be 3 out of 6, which is also 1/2. So now let's look at the probability that A or B happens. So if we think about when does A happen? A happens when we have a 4 or a 5 or a 6. And B happens when we roll a 2 or a 4 or a 6. So how many different ways are there for A or B to happen? Well, I count, we can roll a 4, a 5, a 6, or a 2. So there are 4 different ways for A or B to happen. Notice that if we get a 5, only A has happened. If we get a 2, only B has happened. But if we get a 4 or 6, that means that both A and B happen, since we rolled a 4 or higher and an even number at the same time. So there are 4 different ways for this to happen. 1 way for only A, 1 way for only B, but 2 ways for both A and B. Again, since there are 4 ways for A or B to happen, and there are 6 possible events, simple events, that means that there's a 4 in 6 chance of getting A or B, which we can simplify to 2/3. Likewise, when we look at the probability that A and B happens, we need to look at how many different ways are there to get both a 4 and higher and an even number simultaneously. So in order to get something in this set and something in this set, we could roll a 4 or a 6. So only with a 4 and a 6 is it going to be 4 and higher and an even number. So there are 2 ways to do that, 1, 2, and there are 6 possible dice rolls. So that leaves a 1 in 3 chance of getting both A and B to occur. So there is a formula, and I want to describe why this formula kind of makes sense. So the probability that A or B occurs is going to be the probability of A plus the probability of B minus the probability of A and B. So when you're counting the probability that A or B happens, well, we could have A happen and we could have B happen. So we count the number of ways that A happens and we count the number of ways that B happens. But if we do that, we have overcounted. If we come up to this, let me erase some of my circles here. If we count the number of ways that A or B happens, there's 3 ways for A to happen, and there are 3 ways for B to happen. But we didn't add 3 and 3 together to get, A or B happens 6 out of 6 times, because we double counted. The 4 and 6 appeared twice. So, in order to avoid double counting, if you count all the number of ways that A happens, count the number of all the ways that B happens, we have counted those that appear both in A and B twice. So this is to avoid double counting. So let's do an example. Just more examples, I think, is more helpful. So we've got some drug trials, and some people were given medicine, some people were given a placebo, some people improved, and some people didn't improve. So we've got numbers for each one. So we can ask, what is the probability a random person selected from the trial received the placebo? So what we need to do is count how many people received the placebo, and we'll divide it by the total number of people in the study. Well, there were 71 people that received the placebo and improved, and there were another 69 people that received the placebo and didn't improve. So this is the total number of people that received the placebo, and we'll divide by the total number of people in the study. Well, there were 71 people that received the placebo, plus another 69 people that received the placebo. There were 106 people that received the medicine and improved, and another 34 people that received the medicine and didn't improve. So in total, there were 140 people that received the placebo out of 280 people in the trial. And this is pretty simple. This is simplifies to 1/2, which is going to be 0.5. So what's the probability that a random person in the study received the placebo? Half the people. So there's a 50% chance that when you select someone from the study, they received the placebo. Now let's look at what's the probability that a random person in the study received the placebo or didn't improve. Okay, so now we have to count, okay, how many people received the placebo and how many people didn't improve. When it's arranged in a square like this, this is going to be a lot easier. So this is a helpful trick when solving some questions. So how many people received the placebo? Well, we already counted that before. And if we want to know how many people didn't improve, well, that would be referring to all of these people. So all we have to do is count how many people received the placebo or didn't improve. We have 71 people received the placebo and improved. Another 69 people received the placebo and didn't improve. And another 34 people received the medicine but didn't improve. So this is the collective total of all the people that received the placebo or didn't improve. There's 71 people that received the placebo and improved, 34 people that didn't improve but received medicine, and there's 69 people in this overlap between them. So this is the total number of people that received the placebo or didn't improve. Out of, as what we saw in the previous example, there were 280 total participants. So this adds up to be 174 out of 280. This is a pretty big fraction, so if we round this will be about 0.62. So here's the answer. What's the probability that a random person in the study received the placebo or didn't improve? Well, it's referring to anyone in these red circles. Now, the very last thing that we'll talk about are disjoint events. And disjoint events are events that can't occur simultaneously. One way to think about it is they don't overlap. And I think it'll be clearer when we have some examples. So if we roll a die, we could look at rolling a 3 as one event and rolling a 4 as another event. Well, these two events can't occur simultaneously. You can't roll a 3 and a 4 at the same time when you only roll one die. So these are disjoint. Rolling an odd number and rolling a 4, okay, there's a few different ways you could roll an odd number. You can roll an odd number by rolling a 1, 3, or 5, but rolling a 4, they don't overlap. So these are, in fact, disjoint as well. And then we could talk about rolling an odd number and rolling less than a 4. So I think it'll be easiest to sort of draw a picture here. So what are the ways that we can roll an odd number? Well, we can roll an odd number by rolling a 1, a 3, or a 5. But what are all the ways of rolling less than a 4? Well, we could roll a 1, a 2, or a 3. So over here we have all of the odd numbers, and over here we have all the numbers that are less than 4, and we see they overlap. So these are not disjoint. So drawing a Venn diagram like this I think is helpful, but essentially the question that you're asking is, can both of these things happen at the same time? You can't roll a 3 and a 4 at the same time. You can't roll an odd number and a 4 at the same time. But you can roll an odd number and a number less than 4. So in that last case, they are disjoint. So one thing that happens is if A and B are disjoint, that means they can't happen at the same time. So the probability that A occurs and B occurs at the same time, well, that's 0, since it can't happen. Probability 0 implies something is impossible. So one of the nice things is that if you have disjoint events and you want to calculate the probability that A or B occurs, normally the formula would look like this, where you find the probability that A occurs, add it to the probability that B occurs, and then you prevent yourself from double counting by subtracting the probability that A and B happen at the same time. But if the probability that A and B occur at the same time is 0, subtracting 0 for something doesn't change it. So we might as well get rid of it. So this means that adding probabilities for disjoint events is quite nice. You just get to add them together. Sort of like one quick aside, whenever you see the word or, it means that you're going to be adding things in mathematics. This is just a very common rule of thumb. The word or will imply addition. And then the very last thing in the last couple seconds here, A bar is the complement of A. So if A is the event that something happens, A bar is the event that same thing doesn't happen. So they are essentially opposites of one another. So what's the probability that A or A complement occurs? Well, one of them has to occur. So this will always happen. And this means that the probability of A plus the probability of A complement is always